Okay, let us now apply what we have seen to the quadcopter. So the quad configuration that we have here is the plus configuration. You also have other configurations such as the X configuration. As the name suggests, quadcopter means 4 rotors, and they are numbered here 1 to 4. And you see that rotors 1 and 3 are turning clockwise, whereas rotors 2 and 4 are turning counterclockwise. As we have seen previously, we will be using a reference frame that is attached to the quadcopter, and that is the so-called body frame. You will see if you take your right hand and you point your thumb in the direction of Z, that you're going to from X to Y. You can do that for the other directions, X and B, and XB and YB also, and you will see that the reference frame that we are using is indeed right-handed. Okay, here it's a right-handed coordinate frame, and the Z-axis is pointing downwards. This is often so in applications with flying objects such as a quadcopter. Okay, so you have in blue the 3 variables in translation, right, here attached to the body frame, and as we have seen before, you need 3 variables for rotation, right? So let's take the first one, yaw. Remember, you have yaw, pitch and roll. Yaw is phi here, and as I said, well, if you're pointing downwards, you will see that the natural curl of the fingers goes in the direction of a positive yaw, and so a positive yaw is as shown on the screen. And how can you obtain a positive yaw? Well, you have to make sure that the rotors 1 and 3 are turning faster than the rotors 2 and 4, and that will produce a yaw. The next one is pitch. Okay, so again, if you take your right hand and you have your thumb going into the YB direction, the natural curl of the fingers suggests a positive pitch as indicated on this slide, right? And how can you have a positive pitch? Well, you have to make sure that rotor 1 is spinning faster than rotor 3. And then the last variable is the roll, psi, right? And again, if you take your right hand, you point it in the direction of XB, the natural curl of the fingers goes in the direction of a positive roll, psi. And if you want a positive roll psi, you have to make sure that rotor 4 is spinning faster than rotor 2, right? And then you have the quantities T1 to T4. They are the thrust that is obtained from each rotor, and of course it's influenced by the rotation speed. Okay, let's have a look at the motion of a quadcopter. The first thing that we have to define is what is called the hover speed. So if all rotors are turning at that speed, hover speed, well, the thrust that is obtained is exactly compensating gravity, so the quadcopter will be hovering. It will mean that the height of the quadcopter above the ground will remain the same. So these are the green arrows. If you see a green arrow, it means that that rotor is turning at the hover speed. Then the ones in red, they are a little thicker. It means that the speed is above the hover speed. And the ones in blue, it's a thin line. It means that the speed is below the hover speed, right? So if all rotors are spinning at the hover speed, then it's hovering. And of course, if you have all rotors above, spinning above the hover speed, well, it will go up, and this is, for instance, what you need at takeoff, right? Or if you want to change height, of course. So this is hovering, taking off. Of course, if you have all rotors with a speed that is below the hover speed, well, the quadcopter will go down, as you can imagine. So now you can have a look at pitch control, and we have already discussed this in the previous slide. Pitch control is about changing the speed of rotors 1 and 3, and we have seen previously that if motor 1 is spinning faster, you have a positive pitch. If it's motor 3 that is spinning faster, you have a negative pitch. We have seen also that the roll is influenced by motors 2 and 4. If motor 4 is spinning faster, then you have a positive roll, and if it's motor 2 that is spinning faster, you have a negative roll. Okay, and yaw, well, you have to work with all 4 motors, and if the sum of the hovering speeds of motor 1 and 3 is higher than the sum of the speeds of motor 2 and 4, you have a positive yaw. Okay, and of course, if you want to have a negative yaw, you have to do just the opposite. Okay, let's talk about the thrust force. Well, the thrust force is the upward lift force that is generated by a rotor, and of course you can imagine that somehow it is linked to the angular speed of the rotor, and in fact you can show that it's the angular speed squared times some constant that we'll call the propeller lift coefficient, right? So this is the thrust force for one rotor, and of course the total thrust, well, you have to make the sum for all 4 rotors. Okay, you remember that in our body frame, the z-axis was pointing downwards. Okay, so you need a minus sign over here, right? So we'll say that the total thrust is pointing upwards because of the minus sign, and this variable here, it's the sum of the 4 individual thrusts. Okay, as you often do when you model a system, especially if you want to model it for control, well, you assume that you have the main dynamics, and here the main dynamics will be the dynamics of the quadcopter, and then you have dynamics that are much faster, and these are of course often neglected, and we have been doing this also for our mobile rotor. Remember that we neglected the motor dynamics. Well, here we'll do exactly the same. So we'll simply assume that the square of the angular speed is proportional with some constant that we'll call Cm to the applied voltage, right? You can imagine that the input of our model will be the 4 applied voltages and the voltage applied to each rotor. Okay, remember that if we want to model our quadcopter, we'll have to use Euler's equation, and Euler's equation involves torques, right? So we'll need the yaw torque, the pitch torque, and the roll torque. The yaw torque will be determined in the next slide. So we'll concentrate here on the pitch and the roll torque. So just to see how we obtain this equation, let us draw the configuration of our quadcopter. Okay, this is rotor 1, this is rotor 2, this is rotor 3, and this is rotor 4, right? Each rotor has or produces a thrust. T1 to T4 as shown on screen, right? You have here our center of mass, okay, and also the origin of our reference frame. So we had something like this, something pointing downwards, and then something pointing in this direction. So this is xb, yb, and zb, right? And then we can also show, maybe first start with the first one. So that's yaw, okay, this is phi, this is yaw, and then you have pitch, this is theta, and this is pitch, and then you have roll, okay, and this is psi, roll. And now we are interested in the pitch torque and the roll torque. Well, you have a pitch torque if, and if it will be positive, if T1 will producing, or rotor 1 will be producing a thrust that is higher than that of 3. So here it should be not T1 of course, but it should be T3, right? So if T1 is bigger than T3, we will have a positive thrust. And of course what is important here is the distance that you have from the center of mass to each motor, and we'll call that L, right? So the 4 distances are equal by construction and they are called L. Okay, so it's kind of obvious that the pitch torque will be this, and then you plug in your formula here that you know for thrust. It's kt omega 1 squared. You do the same for T3, you obtain this formula, and then you know that you neglect the motor dynamics, so you can replace W1 squared by Cm V1 squared. V1 is the voltage that is applied to rotor 1. You can do the same for T3, omega 3, and then you obtain this formula, right? Then we do something similar for roll. You'll have a positive roll torque if the thrust T4 is bigger than the thrust T2, and then you obtain this formula. Okay, we had seen that each rotor was producing a thrust 1, 2, 3, and 4, right? So the thrust was upwards, but each motor will also produce a torque, and this torque we'll call it, so this one will be in this direction also, and here you have a torque in the other direction. So this is tau 1, this is tau 2, tau 3, and tau 4. You can show that each torque around the rotor axis is also proportional to the speed of the rotor, but the constant in front is different. Previously for thrust we had kt, and here we'll call this constant k tau, and it's what is called the propeller drag coefficient, right? There is also an additional term that is proportional to the variational speed of the rotor, so the acceleration, but generally this term is neglected, right? So if you want to see the torque, it's now the yaw torque, which was defined like this, right? Well, it's the sum tau 1, tau 3 minus tau 2, tau 4, right? So I've not written it here, but this torque, this yaw torque is tau 1 plus tau 3 minus tau 2 minus tau 4, right? So now we can plug in this thing here, right? And we obtain this thing. And now we remember that we neglect the dynamics of the motor, so W1 squared, for instance, will replace it by Cm times V1 squared. This is the voltage applied to rotor 1. Okay, so here we defined the states of our model for the model of the quadcopter. Remember that we had 6 degrees of freedom, 3 for translation, and 3 for rotation. Okay, we know that if you have 6 degrees of freedom, this will involve 6 variables, right, for the variable itself, and then plus 6 variables for the derivatives, right? So in total we will have 12 variables. Okay, so for the 6 degrees of freedom, we'll choose, and this is a convention, you could choose other things, right? For the translation, we'll choose to work in the inertial frame, so we'll use the variables x, y, and z. And for a rotation, we will be using the Tait-Bryan angles that are used very often for flying objects. In some other papers you will find the Euler angles. These are these angles that I've skipped in my presentation, right? So now we have translation variables and here rotation variables, and now we need to take their derivatives. So we could take, for instance, x dot, y dot, z dot, but very often what we will do is use the linear velocity but in the body frame. Okay, so for position of center of mass we work with the inertial frame, and here we will work in the body frame. So this means that we'll have to go from one frame to another. So we could use the derivatives of these one, right? But what we'll do is work with the angular velocity in the body frame. Okay, remember that this is the angular velocity vector and it has 3 components, right? So these will be my 12 variables for the state of my quadcopter model. Okay, let's start with the model of our quadcopter, and we'll start in translation and we'll work in an inertial frame. Since we're working in an inertial frame, we can use the second law of Newton. So mass times acceleration is equal to the forces that are acting. The m that was here up front, I've put it and I've divided by 1 over m, so it has disappeared over here. So you'll have basically 2 terms that will be acting. You have this term here, it's gravity, and then you have this term that is acting. Well, this is coming from the total thrust, right? Well, gravity is acting in the inertial frame. Don't forget that we have an inertial frame with the z pointing downwards. Okay, so gravity will not give any contribution in the x and y direction, but in the z direction, right? So this is why we have this term over here. Okay, the thrust is pointing in the directions minus z, but in the body frame. Okay, so in the body frame, the thrust will be 0, 0 minus the total thrust, right? But this is here in the body frame. So it's kind of easy. We've seen previously that there is a transformation that goes from body frame to local frame. And we'll use that. Where do I see this? Well, it's over here. Okay, local to body was this matrix A, okay, and body to local, well, it's A inverse, but since this matrix is orthogonal, you can use A transposed, okay? So if you do A transpose times this vector, well, you'll be selecting the last column of A transpose, or the first row of A, right? And this is exactly what is done over here. Then you could add a term that is proportional to the derivative of x, y, and z to add some aerodynamical effects. Okay, this is only valid at a low speed. At high speeds, you should also add effects like drag. Okay, but this is not so important for this model. Okay, so now we want to have to model the rotational part, right? So we will have to use Euler's equation, right? We have seen the full Euler equation, but we've also expanded this equation in the case where the inertia matrix becomes diagonal. Well, it becomes diagonal if you choose, like a reference frame, the principal axis. So you have to pay attention when you define your reference frame that it's according to the principal axis, so that you make this inertia matrix diagonal. If you do so, you can write down the expanded version of Euler's equation. And what you find in here are things that you know because they have been defined previously. Here you have the roll torque, pitch torque, and the yaw torque. Okay, these are the moments of inertia that are appearing in your diagonal inertia matrix. And here you have, well, the angular velocity vector as components omega x, omega y, omega z, and here it's the same vector but you take the derivative, so this is the acceleration in rotation vector. Okay, here is your model. It's the model of the quadcopter. So the inputs are the rotation speeds of the rotor. Of course, you could say that you, because they are linked, use the voltages V1 to V4. In any case, using these, you can compute the total thrusts, right? And you can compute the three torques, the yaw torque, pitch torque, and roll torque, right? So what you see here above is the first equation in translation, right? That we've had, I think, 2 slides ago, with here the contribution of gravity, and here the contribution from the thrusts. This is the thrust here in the body fixed frame, and then we transform it. Yes, this is A transposed, and you'll transform it to the local frame. Okay, and so this is the contribution of the thrust. If you integrate it twice, you have x dot y dot z dot, and then you integrate it again and you have x, y, and z, and this is the position in the inertial frame given by the 3 states. What you see here in blue are the states of your system. This is the little part here with the aerodynamical effects, right? And this is the speed, but in the inertial frame. I've used, and it's often done like that, the speed that is in the body frame. Okay, so you have to take this one here and use this transformation local to body frame, and this is my matrix A, right? So here on top you have everything that has to do with translation. Here below, what you see implemented here is the expanded version of Euler's equation. Okay, and remember it starts from the torques, yeah, and it produces this vector, which is the acceleration vector in rotation, right? If you integrate once, okay, I have not told you it's an integrator here, but you have 3 values in the vector, so it's an it's a vector integrator, sorry. So if you integrate this one, you have the angular velocity vector with its components omega x, omega y, omega z, and these are again in the state of my model, right? We had seen previously that there is a link between these components of the angular velocity vector and that you can transform them into the derivatives of the Tait-Bryan angles, right? And why do I need these? But because I need the Tait-Bryan angles because they are in my state. So I need to take these, which are obtained from these through these formulas here, right? I integrate them and then I obtain the Tait-Bryan angles. Okay, so I have now my 4 states, right? And these ones I have to use because they are coming into this thing here, the transformation local to body, and here body to local, right? This involves trigonometric functions of these variables, okay? And these ones go in here also, because to go from this one to this one, you can see you need C, you need theta, right? Well, that's it. This is the model of the quadcopter, and with this thing here you can go to Simulink and start simulating the process. This type of model can be used if you want to do a control around the hovering position with angles of theta and psi that are not too large, okay? Because if you look in the literature, you will see that if the angles are too large, sometimes you'll have sines and cosines that will go to 0, and you'll end up in a lock situation in your model. So if you want to use this model for control around the hovering positions with pitch and roll angles that are not too big, this model is okay. If you want to use this model to have your quadcopter doing acrobatics, well, then this model is not suited. You will have to go to a model that is more complicated, and it involves what is called quaternions, okay? This is far beyond the scope of this course, but if you're interested, you're going to have a look in Google, your best friend.